Welcome back, Calculus, to the third portion and last examples for the optimization lesson. So we are going to get into some really unique scenarios that pull on prior knowledge that may not be memorized. For example, the equation of ellipse and what an ellipse is and what an ellipse looks like. A rectangle is to be inscribed in the ellipse given by the equation. What should the dimensions of the rectangle be to maximize this area? And what is the maximum area? So an ellipse with this format, you can see the 4 in the denominator of the x. This is going to be a horizontal ellipse centered at 0, 0. And then the 4 represents your width squared. And then you can imagine under the y there's a 1. So if we were graphing this ellipse by hand, we would go 2 to the left and 1 up before drawing our ellipse. I should have made this much, much bigger. So I might blow this up a little bit. And so this is the ellipse inscribed by this equation, or included by this equation. So let's blow it up a little bit. And then we need to imagine inscribing a rectangle inside. So here's a rectangle. And the question is, what should the dimensions of the rectangle be to maximize the area of it? And so we know that the area of a rectangle is length times width. And I'm going to bring back my x and my axis. Whoop, whoop. And so we're just going to pick one of the variables, and it doesn't really matter which one we pick. So w, for example, this point right here is defined by the equation above it. Okay, so you can see this point right here is x comma y, but it's being defined by the function that we were given. So if we really wanted to, we could solve for y and have this point both in terms of x. But if this point is x comma y, then we know that the length is 2x, and we know that the width is 2y. That's y above and y below, x to the right and x to the left. And since we're trying to maximize the area, if area equals length times width, in this problem, area equals 2x times 2y. And then we have some restrictions. X must be less than, this one out 2, and x must be greater than 0. And y has to be less than 1. So let's go to our function above. We have x squared over 4. Now we could choose to solve for x or y, but I'm going to choose to solve this equation for y. Y squared equals 1 minus x squared over 4. Y equals plus or minus the square root of 1 minus x squared over 4. And so for our example, we're just going to use the positive y. You can see that there's a positive and negative y. We don't need both of them to find the area, and area makes more sense when everything's positive. So we've got 2x times the square root of 1 minus, and how you choose to simplify this and how you choose to derive this is really up to you. We have a lot of options. We could get the 2x underneath the radical by re-envisioning it as the square root of 4x squared. We could get a common denominator with the radical. We can use product rule. There's really just a lot. So I'm going to go ahead and use product rule because that's a technique I've been implementing so far. This, though, seems like it would be really efficient. So for product rule, we're going to take the derivative of 2x times the radical plus 2x times the derivative of the radical. And because it is chain rule, I'm not going to put the denominator as 1. 2 square root of 1 minus x squared over 4. And then the derivative of this is negative, bring down the 2, 1/2 x, like so. And so these 2's can cancel. And we need to get So we need to do some arithmetic here. So I'm going to set this equal to 0. Just imagine this is brought down as is. Now I'm going to multiply everything by the square root of 1 minus x squared over 4 because that's going to get rid of that denominator. So we've got 0 equals 2. When you multiply a radical to itself, the radical drops off, cancels out, leaves you with the argument, plus this radical is going to cancel with the denominator, and that's going to leave me x times negative x over 2. So instead of a plus, let's do a minus negative x squared over 2. And this is actually a nice quadratic to solve. So go ahead and distribute out the 2. We've got 2 minus x squared over 2 minus x squared over 2. If you combine two halves, you get one whole. So basically x squared equals 2. And we find that we're going to maximize this area of the rectangle when x is equal to 2, which means the dimensions are 2 radical 2 by, we don't know why. So let's take this and plug it in for the value of y right here. Y equals the square root of 1 minus 2 over 4, which is the square root of 1/2, which is 2 radical 2. Sorry, radical 2 over 2. So then we know that the other dimension is just radical 2. And so what is the maximum area? Well, if you do 2 radical 2 times radical 2, your area max is 4. Ta-da! Let's head to the last example. A rectangular box with a square base, an open top, and a volume of 216 cubic inches is to be constructed. There's my box. Volume equals 216. What should the dimensions of the box be to minimize the surface area? And what is the minimum surface area? So this is not a lot of information. We're going to have to be really clever with how we write our formulas. So first off, I know volume is equal to length times width times height. So here's length, width, and height. And then I know in this problem that that's equal to 216. Oh, I missed a detail, and I'll bring it back in a second. You may not have missed this detail. And then the surface area with the open top. So the surface area is the area of each side. So we've got the base, which is length times W. Then we've got the left and right panels, which are WH, but there's 2 of them. And then we have the front and back panels, which are LH. And there's 2 of them. Now I'm going to go back to the problem. I'm going to switch colors to lime green to make this really obvious. Square base. That means I don't have a length and a W. I just have one of the 2. So I'm going to turn all my L's into W's. All of them. Every single W. And then I'm going to resimplify my equations. So this one is going to become 216 equals W squared H. And then my surface area is W squared for the base. And then all of these sides are the same, so there's really just 4 sides, like so. So from here, surface area is what I'm trying to minimize. And I've got 2 variables, but I also have a secondary restriction equation that I can use to help. So I'm going to take this restriction equation and I'm going to resolve it for H. It doesn't really matter if you solve it for W or H. I'm choosing H just because H is simpler to isolate algebraically. Now my surface area is W squared plus 4W times 216 divided by W squared. That is going to simplify, so first thing I want to know is what 4 times 216 is, which should be 864. Yep. The W's will cancel. And then we're going to take the derivative of this. So the derivative of the surface area is going to be 2w minus 864 over w squared. Set that equal to 0. Multiply everything by w squared. 2w cubed minus 864 is equal to 0. 2w cubed is equal to 864 if you add that. W cubed is equal to 432. And there's a chance that's a perfect cube, but there's also a chance that it's not. And we're just going to get a decimal value here. Yep, it's not. So we know that the width is 7.5595. So I'm going to go ahead and round that to 560 inches. And then I always like to check my answers because I do have a lot of information here. So if the width is 7.56, then the height has to be 216 divided by 7.560 squared. And I'm actually going to use the store answer feature of my calculator. So I'm not going to use that rounded value. I get the height is 3.7797, which is rounded to 3.78. And then what is the minimum surface area? So that means plugging these values into our surface area formula. And it doesn't actually matter which one you use because you do know H and W now. So just pick one. Surface area is equal to W squared, so 7.56 squared plus 4 times 7.56 times 3.78. And so I'm getting a minimum surface area of 171.46 square inches. All right, and that concludes the video notes for optimization. So thank you for watching, and make sure you practice these and send me any questions that don't make sense.